thank you again, and I'm just going to give a short talk here on tailing storage facilities. If we have a mine, we very likely have a waste product. If we have that waste product, we have to put it somewhere. In most instances, for many of the mines here in Ghana, with the exception of one, that process includes tailings, the other being a heap leach pad. So the question is, how do we safely and accurately and appropriately manage these tailings facilities throughout their life cycle? Because we have to have somewhere to put these, and we talked about responsible closure and rehabilitation. So kind of from the planning phase through to closure. So here's a brief outline. So what is a tailings storage facility? If we don't know what tailings facilities are, if we don't know how to handle them, we all think they're very different things. So to a mine operator, it's simply a waste dump. It's always a challenge. It's always potential for water storage. It's always a risk. For a design engineer, it's solids retention, it's water retention. And because I like designing these things, I think they're really interesting. From a regulatory agency, it's a risk to the community. It's a risk to the environment. We understand that it's necessary for development, but we also understand it's long term. Once we tear down the mill, once we tear down all the processing facilities, once all the equipment's gone, the only thing that's left is the tailings facility. For an owner, it's sunk cost. It's always too small, and it's always in the way. I don't think I've worked on a single project where the high-grade deposit wasn't located directly below the tailings facility. For an investor, it's a risk without reward. It's not well understood, although that's changing. And it's a big cost item. It's one of the biggest costs on the mine, but it seems to get the least amount of attention. But when something goes wrong with a tailings facility, as we found out earlier this year with the failure of the dam in Fajau, it's a big deal. 270 some people lost their lives because there was a tailings dam failure this year. In reality, a tailings facility is all of these things, and it's much more, okay? And a successful project from the life cycle point of view for a tailings facility requires that everyone on the project team has the same goals. The design engineer has to be aligned with the owner has to be aligned with the regulators have to be aligned with the project goals, okay? And a life cycle of the tailings facility is important to understand. When, where, and how do we conduct the necessary studies? How does the past influence the present? And how does that influence the future? For instance, now there's a big discussion on upstream raised tailings dams. That's what failed in Fajau in Brazil earlier this year. Should they be outlawed entirely? In Brazil, currently, there's legislation that says any upstream raised dam has to be retrofitted to be a downstream raised dam. All of those dams need to go have giant rock walls built on the outside of them. And it's going to come at a huge cost to owners. If that were to be implemented here in Ghana, how much would that cost our mining industry? Should it? How can we anticipate plans for closure? That's a huge one. And what happens when and not if, because changes always happen, okay? Are we prepared for them? Typically throughout the life cycle, we start off with a conceptual design, a piece of paper, some crayons, maybe some markers, maybe a ruler. Then we go into engineering design, laboratory testing. Then we go into construction and commissioning, operations and changes, and then we talk about closure and post-closure. What's the legacy that's going to exist in perpetuity? And when we talk about the project, we can't talk about the project without talking about the project team. And without a successful team, you cannot have a successful project, okay? So while changes might occur, we need to make sure the core of that team stays intact. And you'll see this little diagram here. The project sits in the middle because the project is what's driving the teams forward, and it's what's informing the teams of the decisions that need to be made. Typically, we have an owner that may or may not be the same person as the operator. We've got our regulators, our contractor, and our design teams. For all the aspects of the mine, you could make this same schematic. And there should be different arrows between, say, the contractor and the operator and the design team. I would just get a bit busy here. But the key is that everybody's in communication throughout the process. Otherwise, we put ourselves at a huge risk, okay? If the operator isn't in touch with the contractor and they don't have communication going, we might be building something we don't need, or we might be without a facility that we have to have. So we start off in the conceptual design phase. So the best place to start is always at the beginning. We need to know what the process tells us about the project. Is it a heap leach pad? Then we don't need a tailings facility. If it is a tailings facility, what do we know about the process? Is there acid generation potential? Are there leachable metals? Or is it just a flotation cell? What locations are available? Have we done condemnation and sterilization drilling on our site? Do we have the right materials and at the right time? If we plan on building our tailings facility from waste rock coming out of the pit, what happens in the out years when we're no longer producing waste rock? Do we have sufficient materials or sufficient planning to make economic use of the materials available to us? What capacity do we need, and what's the likelihood of that change? Is the life of mine 5 years with a 15-year upside? Or is the life of mine 20 years with a 25-year upside? Okay? And then what concerns do we have? That's concerns from a designer's point of view, from a regulator's point of view, from an owner's point of view. We need to be open and honest with each other so that we can make sure that we solve these problems in an economic and an efficient way. We always want to start big and zoom in. So we have a project somewhere in West Africa, okay? More importantly, we have a project on this particular plot of land, and you can see we've done the sterilization drilling. You can see the drill lines. And then finally, after some alternatives assessments, we've identified one location for our preferred tailing storage facility. We always want to have some backup plans. We always want to have a plan B, plan C, just in case, for instance, we find archaeological sites, or we find protected species within our Plan A area. When we're going through a concept level design, we're doing just that. We're just thinking about the problem. We need to show proof of concept. Effectively, we want to be able to make a go, no-go decision. At this stage, typically, there's very little engineering and geotechnical testing. There might even be limited metallurgical testing. What's the grind size of the tailings? It's surely going to change after the conceptual design, and that's okay, as long as we've built in flexibility into the conceptual design, and as long as we have that plan B and plan C. At this stage, we also want to look at what are the opportunities for alternatives. Alternatives, tailings processing, dewatering, things like that. When we go through conceptual design, this is basically what it looks like. On the left, you'll see 5 or 6 different potential sites. On the right, this is maybe what our dam wants to look like, and here's what the basin might be. We typically are looking for things like embankment height, embankment length, type of fill, type of construction, basin liner, basin area, and a drainage type. Okay? Very big picture questions at a conceptual design phase. Next, we go into the detailed engineering. And as we go through detailed engineering, the level of information required also increases. So that also means our costs are going to increase, okay? As an owner, as a developer. Detailed metallurgical and process engineering should be available at this point in time. We should have our finalized TSF location, or at least our preferred location, detailed. We'll need to conduct site investigations and geotechnical testing for both the tailings, the fill materials, the foundations. We need engineering analyses to inform the design, and it's not the other way around. Oftentimes, civil designers will come up with a fantastic idea, and then we run analyses on it and we find out it doesn't work, okay? We might have gone through this whole study phase, done all the designs, only to find out that it doesn't work. That's why we should be using our analyses to inform the design and not the other way around. We should have development of concepts through feasibility and detailed design, maybe with a bankable feasibility in the middle, depending on what our funding requirements are. We also need a water balance and a dam break assessment. It's only when we add water to the system that tailings dams become problematic. If a waste rock dump, for instance, fails or deforms, it's oftentimes a maintenance issue. It's oftentimes small scale, and it's very rarely a risk to people or the environment. But when a tailings dam fails with all that water in it, it becomes a much bigger issue. Okay, so we need to know how much water is going to be in the tailings facility. Do we have enough? Do we have too much? And with that, we also need a dam break assessment. What were to happen in the worst case scenario if the dam were to fail? Do we have communities downstream that are at risk? What would be the environmental impact? Okay. We design these things not to fail, but we see on average approximately one major tailings dam every year fails. That rate is way too high. Okay. Then we need to tie it all together, and more importantly, we need to be planning for closure, at least at a conceptual level during detailed design. Oftentimes, mine owners, operators don't want to talk about closure because that's someone else's problem. I'm on a 3-year contract. This is a 15-year life of mine. There's 2 people that are going to be running this job between me and closure. So why do I need to worry about closure? When in reality, it's going to be one of the, if not the most expensive piece of the mine. Okay? Mine closure is expensive, and if we take advantage of early planning, we can bring those costs down and we can start spending some of that money while we're still processing, while we're still operating. We say sometimes the tails wag the dog. Okay, sometimes the tailings actually tell us more about the project than the project tells us about the tailings. All right? If we, for instance, have chemical constituents, if we have potentially acid-generating materials, if we've got metals leaching, do we need more thorough basin lining, or do we need more thorough under drainage below our tailings to collect that water so that it doesn't, so we can reduce the risk of impact to the environment? Similarly, what does the process tell us? Are we flotation? Are we carbon and leach, carbon and pulp, carbon and column? Are we looking at thickening or filtration? Those will also inform the tailings facility design. Okay? Similar mechanical impacts. Are we producing gypsum, metals, salt precipitation? Especially in the north, especially in places like Burkina Faso, Mali, where we have very, very dry seasons, what can happen is we can actually develop a crust of salt precipitates on our tailings mass. So we might not get consolidation. We might need more storage than we planned for, simply because of the chemical and mechanical impacts of some of these things. If anybody's worked on a phosphate mine, they've probably worked with gypsum. And gypsum can be terribly problematic. It's a very, very dense particle, but very high void ratio. So the overall density is very, very low. It's real soft material that's very low density, so we need to make sure we have enough storage for it. And then have we also considered all the different alternatives for technology? Have we looked at filtered tailings? Have we looked at paste backfill? Golden Star is currently in the process of installation of a paste backfill plant. It'll be one of the first in Ghana, and it'll be one of the largest in the world when it goes through. Okay? So there are new technologies that are coming out that we need to understand, that we need to think about when we go through our detailed design. And then sometimes tailings are tailings are tailings. Sometimes we just need a basin, we put the tailings in responsibly, and we're done. During detailed design, don't let a good idea get in the way of a great idea. Okay? Hopefully, during earlier phases of design, during the concept studies and early detailed design, we've gone through an alternatives assessment. If not, now's the time to do it. I know it's scary as an owner, as an operator, to think, when I'm going through feasibility study, I shouldn't be doing an alternatives assessment. But there might be a better option out there. Okay? Before you commit to a location, at least visit the site with an experienced, qualified geotech and environmental engineer. Okay? Sometimes the problem with the forest is the trees. Right? Sometimes we have protected lands. Sometimes we have surface issues with natural landslide occurrence or geologic development. As an owner-operator, as a contractor, we might not see those things through the eyes of an engineer. Site investigations. We talked about needing site investigations during this phase of design. We always say pay now or pay later, okay? Site investigations are necessary and they're good for proper engineering. Investigations must include foundations and materials used for construction of the facility. Is there suitable material for a compacted soil liner? Or do we need to consider geosynthetics? A rush order on geosynthetics is going to cost a lot more than the site investigation to prove the need for the geosynthetic, or vice versa. Is geochemistry amenable to a specific liner option, and have we characterized the material sufficiently for proper design? If we do a site investigation and we can increase the downstream slopes of our dam only a little, we can save a lot of money on construction in out year. If the design engineers do not have enough information, either our project risk goes up, and the owners accept that, and the regulators have to accept that, or as a design engineer, our conservatism goes up, which means our cost is going to go up. Flatter slopes on our embankments, shorter dams, more conservative zonation. That's the pay now or pay later component. We talked about designing with engineering analyses. At the detailed design, we should always have seepage and slope stability modeling. Do we need to consider an earthquake or not? The answer is yes. Even in Ghana, where we're fairly aseismic, we have to consider earthquake loading. It's part of the regulations, but it's also part of best practice. Should we be looking at deposition and consolidation modeling of our tailings? What's the achievable density? Once we know achievable density, we know tonnage, we can get a required volume. We need to consider storm and spillway design. We need to have emergency spillways on our tailings dams. We have big rainy seasons. This year in the western region, we're actually experiencing one of the wettest years we've had in a very long time. We had rain 2 days ago, right? Unheard of. So as climate develops, as climate changes, we need to be prepared for that, okay? And a lot of that has to do with storm and spillway analysis and design. Analysis should inform the design, not just confirm that it works. And all facilities must be designed to a local standard, and that's at a minimum. In Ghana, we have a fairly robust standard, which is awesome. But in some of our neighboring countries, those standards are either under development or are limited in scope. It might be one page of regulatory guideline. It doesn't mean we should just go to that minimum standard. Sometimes we need to look internationally. Sometimes we need to look to our friends in Australia, in Canada, that have very thoroughly developed standards and guidelines for tailings facility design. Typically we design from the bottom up because that's how these things are built. What do we need between what is there and what's going to be there, right? What do we need for basin lining systems, groundwater protections, groundwater collection? What do we need for our embankment design? What do we need for secondary confinement? Things of that nature. Now, don't forget the water, as we said before. An embankment deformation only becomes catastrophic when water is involved. That's not always necessarily a pond, but usually a pond is the lead driver there. Water balance is important for operational guidance and stormwater management and planning. It should include a detailed climate study, hydrology, hydrogeology, and process requirements. The more return water we can take from our tailings facility, the less water we're going to store out there, which is a positive thing. And we talked about dam break. Once we know that it works, we can complete the design of the facility. This has to include a detailed set of issued for construction drawings. It has to include a report detailing the engineering analyses to support that design. We also use that to support our permitting requirements. We should be developing operational guidance documents, an operations, maintenance, and surveillance manual, okay, and a detailed bill of quantities used for construction tender. Now, once we have all that documentation in place, we connect the pieces of the puzzle. We make sure all the designers are on the same page. Again, we talked about that one. And once we have it all together, it's ready for permitting. Have we included the necessary regulatory agencies along the way? It's a big question. When do we call our friends the regulators? When do we get them engaged in the project? Do we wait until all the designs are done? Some owners, operators might think yes. My opinion is we get them engaged early and consistently throughout the process. Otherwise, if they have a particular problem with a certain site that you don't know about, we could go through this whole process, go through detailed design, and now we can't build it because we've waited too long to get the regulators involved. We have to go back to the drawing board. Once the permits are in hand, then we go through construction, and hopefully we've thought about closure. Okay? How do we plan to close the tailings facility and when? Do we have multiple tailings facilities in the plan, or is it just one over the life of mine? Do we have a plan for storage of the necessary materials? The topsoil, for instance. Have we stockpiled topsoil, and are we planning on maintaining topsoil so that when we go into closure, we have these materials immediately available? Can closure be brought forward due to unexpected consequences? What happens if gold goes to $800 an ounce again? We have to turn off the lights. Do we have a plan in place to accommodate for that? Because the regulators, the government isn't going to allow us to just walk away. We have to take care of our property. What about water during and after closure? What can we bring forward in life of mine, and how does it fit into the overall plans? So now we talk about construction and commissioning. The best plans hold up until the first shovel hits the ground. Every project on earth has the best engineering available. And then we actually start moving earth around, and we find out that we need to make some plans. We need to make some changes. We need to make some adjustments. And that's okay. We need to have oversight from our engineer, our design engineer, our engineer of record, whatever you want to call them, because we know those changes are coming. If we simply turn over the plans to a contractor, the contractor will build whatever they'd like. We need to have a competent and cohesive construction team while we're doing the work. That includes a project manager, construction manager, and field engineer. And a good relationship is worth its weight in dirt, which it turns out is really expensive. If the contractor and the owner are constantly at odds with each other, the build isn't going to go well. If the engineer on site and the contractor are constantly fighting, the project is doomed for failure. So we need to build those relationships, and we need to have trust in one another. Okay? Here's two small comics that talk about construction planning. The first one at the top, the lady comes up, says, "I need a budget estimate for my project, but I don't have a scope or a design for it yet." The gentleman answers, "Okay, that'll be $3,500,000. The lady goes, "You don't know anything about my project." The gentleman says, "Obviously, neither do you." Okay? We need to know something about our project when we develop cost estimates. We can't just simply say it's a $5 million tailings facility. We can't always rely on rule of thumb, 1.5 US dollars per ton. Those rules don't work anymore because there's opportunities for cost savings, but there's also opportunities for cost overrun. So during construction, we all have one thing in common: get the build done safely. All right? Unfortunately, sometimes that's where it ends. The owner wants to get it done quickly and economically. Economically is in quotes because we all know what that means. Get it done as cheap as possible. Okay? Oh, and hopefully we get it done correctly as well. The contractor, get it done quickly, make my money, go home. Right? And the engineer is solely responsible for getting it done correctly. So you can see where this can cause some issues, can cause some turmoil. But that's where those relationships and that's where that trust really comes in. By working as a team, everyone can achieve their goals and the project can be successful. We need to be aware of external pressures as well. When the GM comes down and says, I've got to cut $1 million out of your budget for the construction, we can't just accept that, because that $1 million will be the difference between a successful and an unsuccessful build potentially. The other piece of external pressures that we need to be aware of is a little thing called value engineering. It's becoming a new phase in studies and study developments. They go through value engineering after it goes through detailed design. And what value engineering is how much money can we cut out of the capital and push forward a few years. They're not actually saving money, they're just pushing money down the road. Okay, so we need to be very careful of value engineering. Now that we've got change design, change intent, the big question is there a mechanism in place to manage changes throughout construction? And the answer should be yes, because changes could be required by the design team, by the owner, the operator, the contractor, regulatory agencies. Do we have a mechanism in place to discuss, to document, and to agree on those changes? And hopefully at this stage the changes will be minor, but they will occur. Now we've got our tailings facility built, which means we can start milling, we can start mining, we can start processing, and we can start recovering money. Okay. Operations and changes. So once we start operating, that's the new phase of the life cycle. Okay. This is when your children start getting up, walking, and running. As we move into the day-to-day operations, we can't get complacent. We need to have in place key monitoring, operational controls, and we need to be using those to see how the facilities are performing. And then again, are we planning for closure properly? On a day-to-day process for a tailings facility, this usually revolves around pond management and beach development and control. Do we need a big pond or a small pond? Hopefully we need a small pond and we can maintain it. There are certain reasons like acid rock drainage where a large pond might be required, but hopefully not. We don't have too much of an issue with acid tailings here in Ghana. Is our facility life tied to our life of mine, or do we need to go to a new facility? Even though things are going great, we should still be in regular communication with the whole team. All right? Just because we've been operating for 6 months doesn't mean we can get rid of our design engineer, doesn't mean we should stop communicating with the regulators. And our operations manual, surveillance manual is a roadmap to success. It tells us what we need to be looking out for in terms of problems. Hopefully we've got enough monitoring going on in the facility. Here you can see some piezometers, both a standpipe and a vibrating wire piezometer, survey prisms, maybe inclinometers. How often are those being read? What do we do with that information? That should all be part of the operations manual. Too often we find that a young engineer, maybe an intern, is responsible for going and collecting this data. That data is very nicely written onto a piece of paper. That piece of paper is put on a folder. That folder is put on a shelf, never to be seen again. That's not good monitoring. Just taking the readings doesn't help. We have to know what to do with those readings. Okay? So here's an example. Here's an embankment with 2 piezometers in it. On the left, you see factor of safety of 1.7, compliant with the LI for a Class A dam. And that's what we were designed to operate under. But as it turns out, if that phreatic surface, if that water level in the dam goes up, we might go to a factor of safety of 0.9, indicating failure. The nice thing is these water levels don't change overnight. So if we're doing proper monitoring, we should see the trends going in the wrong direction and we should be able to make the changes. Okay? Understanding all of the details is not necessarily critical. But it's understanding that if a change occurs, if we see changes happening, who do we contact? Who do we tell? And what does our operations manual tell us? Hopefully we have an operations manual that says if a piezometer is reading one level, we need to contact a supervisor. If it's reading the next level, we need to contact the design engineer. If it's reading the next level, we need to contact the GM. If it's reading a next level, we need to contact our regulatory agencies. We need to enact our emergency response plan. The best test for performance is a functioning facility. We can do all the designs we want, all the engineering analyses we want, but we really need to actually see the facility operating. Okay? Are there opportunities for change in design or operations? If we're getting better performance than we planned, can we reduce the fill quantities in the future? Can we change the design of the facility to save some money? Is a change in the process going to include newer technology? Will we put in dewatering circuits, things like that? And the changes need to be evaluated for merit both on an economic and technical basis. And more importantly, do we still comply with the design intent and do we still comply with the regulatory requirements? Then we go into the closure and post-closure phase. Closure, but we just started. When does closure begin? After the mine closes, when the mill shuts off, during operations, during construction, during conceptual design? The answer is all of those things. When we identify that we want to build a mine, the first thing we should be thinking about is how do we close it? How do we get rid of the legacy? Okay? Planning and execution of closure should begin with the inception of the project. And all stakeholders need to understand the goals of the TSF closure and how it fits in with the overall life of mine and site-wide closure. Have we brought as much forward into closure as is appropriate? Meaning, have we done progressive reclamation maybe of the downstream slopes of our dam? Have we brought in a water treatment facility if we're going to need one in closure? It's cheaper to run it while the mill's still operating and while we still have power being generated than it is after the fact. Okay? And is our walk-away strategy in place for post-closure? When can we return the land back to the rightful owners? Okay? There'll be a nice talk tomorrow afternoon about closure, so I've left this a little vague and a little short. So thank you.